Okay, so now we're going to take a look at how one property in the periodic table, which is the effective nuclear charge, how that influences some of the periodic trends that we're going to see. So the effective nuclear charge we discussed before, we often abbreviate that as ZEFF, Z subscript EFF. And that is the charge, the net positive charge that is attracting a particular electron. And that's going to be influenced by shielding, as we talked about before, by the core electrons versus whatever valence electrons are in that atom. So what's the trend in the periodic table for the effective nuclear charge? Well, as we go from left to right, the Z effective, the effective nuclear charge, essentially the pull that an electron, the outermost electron, feels from or experiences from the nucleus decreases. As we go from top to bottom in a group, so going down a group, the effective nuclear charge decreases. Oops, I'm sorry, I made a slight mistake. Let me clarify that. Going from left to right across the periodic table, the effective nuclear charge increases. That's my mistake, misspoke. So left to right, the effective nuclear charge increases across the period. Going from top to bottom, the effective nuclear charge decreases. So what's the reason for these? Well, going from left to right across the periodic table, what you will notice is that the number of protons increases. Okay, so that's increasing the charge in the nucleus. But we're also increasing the number of electrons. Those electrons that we're also increasing are being added to the same energy level. So that means they're not really good screeners of that nuclear charge. So the additional electrons are not good screeners of the nuclear charge. So in other words, the outermost electrons, they actually feel a stronger pull towards the nucleus, and as a result, if they're being pulled closer to the nucleus, that will affect some of the properties of the elements. Going from top to bottom, you're going down a particular group, the effective nuclear charge decreases, and the reason for that also is very important. We're increasing the number of protons as well as we go down the group, but we're also adding more electrons, and those electrons are being added to a brand new principal energy level. Right? So electrons are added to a new principal energy level, and that means they're going to be very well shielded by those inner core electrons. So they're shielded from the nuclear charge because those additional core electrons are really good screeners. So those outermost electrons now, they experience a weaker pull. The effective nuclear charge they experience is a lot less than elements that are higher up. So those are important reasons to note about the effective nuclear charge, because we can use that to explain lots of the trends in the table. So we talked about what effective nuclear charge is. We described it. But can we put a number to it? Well, we actually can. We can approximate what the effective nuclear charge is according to this equation. So the effective nuclear charge is equal to Z, which is the number of protons. And you can think of S as the number of core electrons. All right, so for example, if we have a lithium ion over here with 3 electrons in it and 3 protons, right? The effective nuclear charge in this case that the outermost electron is going to feel or experience is going to be the number of protons 3 minus the number of core electrons, and we have 2 core electrons here, so 1. So this outermost electron, this one here, experiences not the full +3 charge, but it experiences a +1 charge or a +1 pull towards the nucleus. Right? That's how we want to think of the effective nuclear charge. So we can use that effective nuclear charge to explain, to talk about and to explain the sizes of the elements and the atoms as we go across the periodic table. And the first thing we're going to take a look at is something known as the atomic radius, and the plural of radius is radii, and this is an indication of the size of the atom. Okay, we've approximated atoms to be roughly spherical entities. Okay, so if I have an atom like this with the nucleus at the center, okay, then as you may remember, the radius of something, of a circle, is just that distance that we have there. So the bigger the radius, or the larger the radius, the bigger the atom is. There are a couple ways by which atomic radii are represented. We have what's known as the van der Waals radius, which is when we have atoms that are right next to each other, but they are not bonded to each other. So for example, if we have krypton over here on the left side, and we have those krypton atoms that are just packed really, really, really close together, well then the radius is going to be this distance there, from the center of one atom to the outer edge of it. We also have the covalent radius, which is the radius we look at when atoms are bonded to each other. So for example, in bromine, which is made up of 2 bromines linked together, the radius there would be the distance from one nucleus to the other, and we divide that by 2. All right, so that distance is 228, and pm is picometers. We divide that by 2, and we get this distance here as the covalent radius. All right, so when we talk about the radius and the atomic radius in a general sense, it kind of depends on whether we're looking at non-bonding or bonding radius, but the idea is the same. Right? We're looking to see the size of the atom. And again, size is here in pm. Pm represents picometers. 10 to the negative 12. All right, so what's the trend in atomic radii as we go across the periodic table? Well, we see that as we go across from left to right, the atomic radius decreases. In other words, the atom gets smaller as we go from left to right. And why is that as we go across the periodic table? Well, we can tie that into the trend in effective nuclear charge. Right, we saw that from left to right, the Z effective nuclear charge increases. Okay, so that means as we go from left to right, those outer electrons are being pulled closer to the nucleus. So the outer electrons feel a stronger pull to the nucleus, and as a result, if they're being pulled more strongly towards the nucleus, they're going to be closer to the nucleus. And as a result, the radius is going to decrease, which would make the atom smaller. All right, so that's the reason for the smaller atomic size as we go from left to right. We go from top to bottom, going down a group, we see that the atom gets bigger. Going down a particular group. Okay, and what's the reason for that? Well, we can tie in the effective nuclear charge as well, right? As we go down a group, the Z effective decreases. So the outer electrons feel a weaker pull to the nucleus. In other words, they're not being held very strongly. And as a result, they can be further away from the nucleus, which then would mean that the radius increases, or the size of the atom increases as a result. All right, so the sizes of the atoms can be explained by the effective nuclear charge for those outermost electrons. When we and again, we're looking here at the trends for the main group, or the representative. Elements. When we get to the transition elements and the intertransition elements, the trend isn't as obvious. There's some exceptions. There's some anomalies when we encounter those, and that's because those electrons are filling in the D and the F sublevels. So when we look at our electrons, not just the valence electrons, but now all of the electrons, and we arrange them, we configure them according to the rules of the Aufbau principle, the Hund's rule, Pauli exclusion principle, and we do our electron energy or orbital diagrams, drawing the electrons in as arrows. We're going to encounter a couple of situations. We're going to see either our electrons are all going to be paired up in our orbital diagram, or we may have unpaired electrons. So when you have unpaired electrons, that actually means that that particular species, atom or ion, will have a net magnetic field, because that unpaired electron doesn't have another electron to counter it. So we refer to that as paramagnetism. And what that means is that chemical species will be attracted to a magnetic field, right? So that's a physical property of a chemical species, the fact that it interacts with that magnetic field based on the electrons being unpaired. If all of the electrons are paired, then we refer to that as diamagnetism, and that chemical species will actually be repelled by a magnetic field. So we can actually use that magnetic field, observe what happens to that chemical species, and we can predict whether the electrons are paired or whether they're unpaired, and we can then tie that back into some of the anomalous or unusual electron configurations that we saw previously. All right, so in some cases, especially when you get to the D block, some of the electron configurations and the orbital diagrams are not what you expect, and that's because we can actually observe them experimentally, for example, in this, and we can make sense of what we observe. All right, so let's take a look now at how the size of atoms and their corresponding cations change as we go across a period or down a group. Generally, what we're going to see is that the cation radius, remember cation has a positive charge, is smaller than the corresponding neutral atom radius. So for example, if you look at sodium over here, okay, the sodium atom itself is in gray, has a radius of 186 picometers. The sodium ion, Na+, has a much smaller radius of 95 picometers. Okay, so Na+ is smaller than a neutral sodium atom. Right, remember, in order for the Na+ to form, Na must lose that one valence electron. Okay, and then once it loses that valence electron, the resulting electrons, the resulting valence electrons, is in a lower energy level, and that energy level is closer to the nucleus. So as a result, that ion then is smaller because that outermost electron is just closer to the nucleus. So as you can see in this particular table, as you go down a group, we're comparing the sizes of the ions now. So the lithium ion, the sodium ion, the potassium ion, the rubidium ion. Down a group, the size of the ion increases, which is the same trend in just the size of the atoms. And then going across a period, so going this way now, we see that the size of the ion decreases, which is the same trend in the size of the atoms, for the exact same reasons that we talked about previously with the effective nuclear charges. What about the size of the atoms compared to their anions? Well, remember, anions have a negative charge. And when an atom forms an anion, we add electrons to it, and we add electrons to the valence shell, right? The valence shell, remember, is the outermost. Valence always means outermost shell. And what does that do to the effective nuclear charge to those valence electrons? Well, the effective nuclear charge now experienced by the valence electrons is decreased the electrons are going to be further away from the nucleus, and as a result, the size of the corresponding anion is bigger than the corresponding neutral atom. So for example, if you look at oxygen here, the oxygen atom in gray has a radius of 73 picometers. We add 2 more electrons to it to complete its valence shell to be like the nearest noble gas. We form the O2 minus ion. Its size increases almost twofold, right? It almost doubles in size because we're adding electrons to that valence shell. We increase those electron-electron repulsions, for example. The electrons get spaced a little bit further away from each other, and the size increases. As you go down a particular group, okay, you can see the size of the ion increases. So if we're just comparing all the green spheres now to each other, they all increase going down the group. As we go across a period, so going from left to right, we can see that the size of the anion decreases slightly.